Okay, so we can continue. We have seen the equation system and the outcome for 0D configurations for laminar premix flames. Now we extend this to 1D instationary laminar premix flames. 1D means when we look at these three different configurations, we can look at a planar flame, and then there are only dependencies in one dimension here. And we again can neglect all other dependencies in the two other dimensions. We can transform this for a cylindrical geometry. So here we have dependency only in this direction, and along this surface there are no spatial dependencies. And we also can transfer to spherical coordinates. The same, we have dependency only in one direction and have no dependencies along the surface of this sphere. So we use in one-dimensional geometry, we have to use spatial discretization with finite differences. We have an adaptive mesh refinement. We use a modified Lagrange transformation, which I explain later, and then we can solve the equation system. So here we have already the transformed equation system, and we assume for this example uniform pressure. So we have a quite simple equation system. So the temporal change of mass fraction and temperature can be described again with the part of the equations we have discussed before here for the mass fraction of species I, for example, again the chemical source term, and here the diffusion flux, and here again the heat conduction and so on. So this we have discussed already in detail before. Now the equations looks of course a little bit different, but this we can solve, and you see here this alpha. Alpha means, so we can use it either with alpha 0, 1 or 2 for infinite cube and cylindrical configuration, or for a spherical configuration. So if we look, for example, at a spherical flame, so we are interested in the along this coordinate in the solution of our equation system, and assume that there are no dependency in this direction. So we need to know the inner boundary conditions and the outer boundary conditions, and we need to know the initial conditions along this coordinate. So we can use here for this specific setup, for example, vanishing gradients at the beginning. That means there is no change of the quantities here at the inner boundary, and here we have fixed wall temperature and fixed wall position. That means we have we can have, for this, if we have fixed wall position, we have a constant volume. Or if we assume a constant pressure, then of course we have vanishing gradients at the outside too, because the system is expanding if we have a combustion take place here in the center. So, and then this flame front, so we ignite here, and then the flame front of course expand from the inner towards the outer boundary. Then we have this ignition source term here, but first we explain again the parameters. Of course, we need to know pressure, temperature, size of the volume before we perform the calculations. We need to know the initial gas composition, and we need to know the ignition parameters. It means to know the ignition volume, ignition energy, ignition time. So how much energy is deposited by our spark, in which time and in which volume. So, and this can be described for our equation system by our source term. So here we have a specific profile for our source term, so the radial profile of Q. This depends here on this factor. Here we can also have a factor of 2 only. We can have a linear relation. Then, of course, you get different profiles. This number of 8 was shown in previous work that it gives sufficient results compared to experimental work. Then we have here the energy density. That means the energy of the spark and the volume of the spark, and the TF represents the temporal length of the spark, so how long we deposit energy into our system. This I want to explain you with a side note here. We talk about now about plasma-assisted ignition. This was an approach to yield large ignition in a larger volume. So when you look at a typical spark plug, you have ignition taking place in maybe over a length of 0.5 millimeter with a radius of 100 micrometer. So in a combustion engine, you have a very small volume where you initiate your combustion. And then, of course, if you go to lean mixtures, which are more difficult to ignite, this may be difficult. In the combustion engine, you have a turbulent flow field. So it's quite difficult then to ignite. And one idea was to use such an plasma-assisted ignition. You see here the large volume where your plasma occurs. So the idea was not to have only a small volume where we start the ignition using a spark plug, but we inside our combustion chamber we ignite the system in a larger volume. So we get rid of the negative effects of our turbulent flow. So the idea is to have reduced ignition delay time, but of course especially to improve engine performance. There are also solutions now in the market where they use commercially available spark plugs where they use this effect. So this is one way to ignite a larger volume in your combustion chamber. But what we need to know when we use this so-called plasma-assisted ignition, what we talked until have discussed until now is thermally controlled reaction. So the Arrhenius type of equations we have seen are dominated by the temperature. And so this here for the specific radicals we are interested in here, OH plus H2 leading to OH plus O. So the reaction rates, of course, strongly depend on the temperature. But if we consider these non-equilibrium plasma, so when we look here, of course, there's something happening inside these discharges. Normally, for spark ignition, we can neglect this because here the temperature is the dominant part. so the heat up inside this spark. But for these non-equilibrium plasmas, we also have to consider this so-called electron impact reactions. So oxygen plus an electron gives 2 oxygen plus an electron. This depends on the strength of the reduced electrical field given here in Townsend. So the higher the electrical field, the more oxygen is produced. And what you see here, that the amount of oxygen we produce, or the reaction rate for this reaction here, is much faster than the reaction rate, for example, for this equation here. So if we have an electrical field, we produce a lot of oxygen atoms with this part here, and especially at low temperatures, we don't produce any oxygen following, for example, this equation. And I'll show you now an example where this is of importance, just to focus on this non-equilibrium part. So of course, when we consider a combustion engine, we have to optimize both. And here the focus is more on the non-equilibrium plasma. And an example here is a streamer discharge. So we have an AC voltage which changes very fast the polarity. So here we have in 3 milliseconds, you see, so we have the frequency of megahertz eventually. And so here we see voltage and current. And you see here in the current some change in the structure. And when we use a proper filter, we can see that there is some current here flowing at these specific positions. So, and what is happening? So we have this strong electrical field. Here we have a pin electrode. Here we have a plate electrode. So we have an electrical field here. We have a very long distance, just to emphasize the effect here. So what is happening? The polarity is changing very fast. So we have a strong electrical field here with change its polarity, but when we have the maximum voltage here, something is happening. So a streamer discharge occurs. So the streamer wants to go from this way from here to here. So this breakthrough wants to occur. However, it cannot happen because we change the electrical field. So the streamer starts, the electrons are going this way, and suddenly we change the electrical field, so the electrons have to go back. And so this we do very fast and very often. So what is happening here? We look at the I think these were OH-LIF experiments. So here we see the streamer discharges. So you can see we do not have at high voltage amplitude, we do not have only one discharge pathway. We have a lot of possible discharges. If we reduce the energy, okay, this focus more or less on one reaction way. And what we do here, we increase the number of voltage cycles. So this is a summary over 50 voltage cycles. Here we have 75, and here we have 150 voltage cycles. And so what appears, so we don't have a spark. So we don't have a classical hot plasma. For each voltage cycle, we have a short streamer discharge for 30 nanoseconds. Then we change the electrical field, so everything disappears. Then we change the electrical field again. Again, we have a very short streamer discharge. And so this streamer discharge, the second one, sees the result of the old streamer discharge. So it prefers to go this way again. So the length increases with time. You see it maybe here or here more in detail. So after 165 nanoseconds, after 150 streamer discharges, this is much bigger than after this time. So we increase the volume where energy is deposited, but we don't have a spark, so we don't have a hot plasma of several thousand K here. But nevertheless, you can see here ignition occurs. Well, here there's a small ignition volume. And so finally here the flame front starts to moves outside into the unburned region. So, and if we would continue this, we would see more or less a spherical flame moving in the unburned mixture. So again, this is not a classical spark ignition where the hot temperature dominates the ignition. Here we have this so-called non-equilibrium plasma. So at each streamer discharge, we deposit only a small amount of energy into the system, and we have these electron impact reactions creating a lot of radicals at quite low temperatures. So what is then the outcome? So this we have examined using a laser setup. So we have this rod plate configuration and send a laser sheet through this. Here we see the electrical parameters, and we then have the gate timing of our laser and camera system, so at which time we look into the system. So here in detail, here ignition takes place, so the flame front starts to, the hot kernel region expands here as a function of time. And for example, we can analyze the flame propagation along this axis here, which is not disturbed from any streamer discharge which has occurred in this region. So we yield then flame front positions for different mixtures here, 15, 20, and 35 volume percent of hydrogen in air. And so we compared first of all our global flame velocities. So the spatial velocity here is we yield with this setup is quite sufficient when we compare it with experimental work or with other work from literature. And so then we can calculate numerically within 1D model the flame front propagation. So you see the flame front propagation from experiment and simulation comparison is quite good. So of course, this is the combustion in the unburned mixture perpendicular or normal to our streamer discharge. So this is not disturbed by any electrical effects. So here we have unburned gas mixture just burning with the normal, well-known flame velocity. So what we can do here now, we can, in the simulation, we can change the energy we deposit into the system. That means we change the ignition delay time. So, and if we do this, for example, we can check, okay, here we have different experiments, which gives better comparison, which simulation gives better comparison with the experimental results, so we get some information about the energy which is eventually deposited into our ignition volume. There's one problem with, maybe problem is not the correct word. So you see this non-spherical shape. So of course the streamer discharge occurs along this axis. So there was something like a preheating here, and we produce, even though we may ignite it only here at the tip of the rod, of course, so we do not have quiescent unburned mixture along this coordinate anymore. There we have also deposited some energy, so it's a little bit hotter here already, and we produce a lot of radicals here. So the flame from propagation in this axis is faster than the flame propagation in this direction. So this can be seen here. So we have either flame front in this direction or in this direction plotted here. So black one is the axial direction. You see this is much faster, but of course, so we have a lot of fluctuations here because this is dominated by the streamer discharges. So here we have a maximum velocity. If we then increase the energy to higher values, we do not see any more an ignition only taking place here at the tip of the rod. We can see that ignition takes place along the whole volume of the streamer discharge. So again, this is the original aim of this application, to yield ignition in a larger volume. So this is why this is a concept which is also examined for combustion engines. So these streamer discharges are characterized by a non-fully breakdown. So we don't have a spark. So we don't have an equilibrium plasma. So we have only low current. We have a temperature increase per streamer discharge by only tenths of Kelvin. So we are talking not about thousands of Kelvin, like for a classical spark, tenths of Kelvin increase for one streamer discharge. The plasma is non-equilibrium, and most of the energy is stored here in the electrons. So we do not heat up the system, but we have this electron impact reactions. So we have a lot of fast electrons, which then lead to a lot of radicals in our quite cold combustion region. So and the question is, how is this ignition influenced by these effects? So normally, if we want to describe in spark ignition, temperature is of importance. This we need to know precisely, and the temperature depends on the energy we deposit into the system. And we can neglect a lot of other phenomena. The temperature dominates the ignition process, but this is not true for this non-equilibrium plasma, and this we can show with the numerical simulation. So first of all, we used the mechanism we use for this specific problem. You see here we have a lot of electron impact reactions included in this mechanism. We compared the outcome of our results here using this black mechanism with literature results. So there are some deviations to other work, but there's a good comparison with here, for example, simulation using the Combustion mechanism. So it's quite sufficient to use this mechanism to calculate ignition delay times for classical spark ignition simulations. So here we have not considered any of these reactions, or we do not have considered this non-equilibrium plasma effects. So this is only the thermal part we focus on, and here we see an excellent comparison. But also, if we use this non-equilibrium plasma effects, we can see what are the important reactions here for our specific system. And so this is, again, well known from literature. Here we have the three important reactions. So O2, N2, and H2 plus an electron gives us nitrogen, atomic oxygen, and atomic hydrogen. So we use this 1D configuration I have explained before. So we have only spatial dependencies along this coordinate. We have now a lot of additional species to consider. Here are the classical ones, nitrogen, ozone here, and so on. So here we have hydrogen also, but you see we have a lot of excited species too. So we do not only focus on the electronical ground state, we also consider excited species. So our electron collides with a nitrogen, and if it's not dissociated, it may be reach a higher electrical or vibrational state in a higher energy state. So this has to be considered. So the energy is not only deposited anymore only into thermal energy, but also a large part of the energy is used for this electron impact reactions. Here you see an example again for this excitation I've explained on the last slide. Then, of course, you have to consider here the enthalpy change, which is outcome of this reaction. So the final temperature, of course, is then a function of this enthalpy change too. So here we have some species with some enthalpy we need. These are the equations we are considering here. So we have 13 reactions where we have this electron impact effect, and of course this has a specific source term here too. So we need to know the strength of the electrical field, we need to know the electron density, and of course we need to know the mixture composition here. And so for the simulation we have a simplification here. You have seen this temporal profiles of voltage and current, and we assume now for the simulation that at specific time we have a streamer discharge. This is what we have seen in this current profiles. Only at very short time, for several nanoseconds, a streamer discharge occur. And so for a simulation we put on this term, or it's for the rest of the time it's zero. There is no streamer discharge. The electrical field is in the range of 100 to 300,000 following literature. So what is then the outcome of this part? So first of all, here we have the electron density. So how big is the number of electrons we have in a streamer discharged at atmospheric pressure? So this is somewhere between 10 to the power of 11 to the 10 to the power of 15. So here we see the mass fraction of the electrons, the radial profile. with a streamer radius in the range of 150 micrometer. So the number of electrons we have can be calculated in this discharge. So what also is important to know at higher temperatures, so we have less electrons, and of course we have lower density, so we have also less collisions. So what is now the outcome? So first of all, here you see the temperature for two different examples. As I said, during one discharge, there's only a small change in temperature. So most of the energy is deposited into this non-equilibrium plasma reactions. So during one short discharge of 100 nanoseconds, there's only a small rise in temperature, around 30 K per discharge in this example. And of course, so if we neglect the plasma reactions, so we only deposit energy for a short time, which heats up our system. We don't have any plasma reactions, so we heat up the system. This is more or less like a classical spark ignition. We deposit only thermal energy. So we heat up the system, ignition, it's the deposition ends, the system cools down in this example, and then the chemistry wins, ignition takes place. So if we decrease the energy here, we won't see any ignition. So this is the limit minimum energy for this example. Then we turn on the electrical field, so we include also these non-equilibrium plasma reactions. And you see the outcome is the minimum temperature we have to reach is much lower than compared to the case where we don't have considered plasma reactions. So the energy is here again. So if we use less energy, no ignition occurs. So this is a minimum energy necessary for ignition. But important is here the difference in temperature. So we can reach much lower temperatures, but still ignition occurs. So because, of course, it's no longer Arrhenius dominated. In this black case, only the Arrhenius equations are of importance. So the temperature is the dominating factor. But here we have this non-plasma, non-equilibrium plasma reactions, the electron impact reactions, also producing a lot of radicals. So how does it look? So here again you see the temperature profile, and here you see the difference when we look at the different species. So black symbols represent the amount of radicals formed during this classical spark discharge. So we heat up the system, and with temperature increase we form more and more radicals, and finally the system may ignite, and so we reach the equilibrium. So we have, of course, this is a function of the temperature we have. In case of an electrical field, we produce a lot of radicals already during the discharge. Even though it's quite cold here, we see that we have huge production rate of the different radicals. So what is important to see is that not only the thermal or the temperature is important now, also in addition this formation of radicals in quite low temperatures is of importance. So we can perform then again reaction flow analysis, which we have seen before in detail in the last lecture. So you see here, during the discharge, these electron impact reactions, for example, for hydrogen and oxygen, are very, very important. So here we have this non-equilibrium plasma reactions, which dominates the formation of O and OH at low temperatures. So here the Arrhenius equations are very slow, but these reactions dominate the system. After a discharge, so again the discharge is 100 nanoseconds, and then it takes some time until the next reaction occurs. We see that the radicals are formed by collisions here, for example, for hydrogen, of hydrogen molecule with excited species. So with this excited nitrogen here, for example, leading then to hydrogen. This is not so. This is also important here, for example, for oxygen. This oxygen collides with this excited nitrogen molecule, leading to atomic oxygen. So again, the radicals are formed at quite low temperatures by molecules which are formed formed mainly within the non-equilibrium plasma. So also even though there is no discharge present, we still create reactive radicals. And then, okay, we reach the high temperature range before ignition. And you see here the classical chemistry dominates the process. So all radicals are formed now more or less by the classical reactions here. We see some small influence of an excited species, but at high temperatures, again, the classical Arrhenius equations dominates everything. So here, the same outcome. So I want to continue now with an ignition by a hot turbulent flow, and I try to hurry up. So here we have an example of a turbulent hot jet ignition, which is also a concept for combustion engine. So the Formula One engines now have only 4 cylinders and so on, but they are still very fast. And one of the things they use is so-called turbulent hot jet ignition. They have a small volume where they ignite their mixture by a spark, and then they have their large combustion chamber, and the small ignition volume is linked to the large combustion volume through a small hole, a small nozzle. So you have an acceleration along this nozzle due to a pressure difference. And finally you get something like this. You get a large volume, very turbulent volume where ignition occurs. So this, of course, promotes the ignition efficiency drastically. So you have, compared to a spark plug where you have a very small volume which you ignite, you have a large volume, and you have also produced a very turbulent field. So a very fast combustion process already set in. So within, you can optimize then, of course, the combustion efficiency also for combustion engines. So, and here we see this again. So here we have an chamber where the ignition with a spark occurs. And here we see a nozzle or an opening. So here combustion takes place, pressure is increasing. Finally, the flame reaches this nozzle, and there's of course a pressure difference between inside and outside. So we have a fast acceleration of the flame. So we have a very fast outflow up to the velocity, sound velocity of the hot gas, so up to 2000 meters maybe. And then we have a very large volume with a very turbulent flow where this ignition may occur. You see outflow and then ignition occurs very fast in a great volume. This is of course also important for flame arresters, where we have the same effect. But for flame arresters, of course, we want to avoid this. So the question is, how do we have to construct here the nozzle to avoid the flame transmission? Of course, if we get smaller here, if we get longer here, we can avoid this flame transmission. So here we do not want to optimize the ignition process. You want to optimize the non-ignition process. And therefore, of course, we need to know from what does it depend. So we, of course, use then a numerical approach because that's the advantage. We get much more information than only from experiments. And we can use this to optimize the setup. So the problem is when we look at turbulent reacting flows. So for laminar case, okay, we have a special discretization, and this can be optimized. And so finally, if we have more grid points, our numerical results gives sufficient agreement with the laminar profile here. So you see we just increase the number of grid points, we get a finer and finer grid, and the agreement is perfect. For a turbulent case, it looks a little bit different. So we have the overall profile, but also we have a lot of fluctuations here. And so then there's a question of calculation time and costs. So if we look at such an LIF image of OH radicals in this ignition event having a turbulent hot flow. So here the hot gas flows out and then the ignition takes place in this volume. If we want to calculate it, so we have to consider different quantities. So how many equations we have to solve if we have to use a fine grid. So it's very costly 3D numerical simulation. This can be done, of course. But if we use a classical laptop for this calculation, if we perform a direct numerical simulation, have a very fine grid, okay, after 190 years, your PhD thesis is maybe finished, or you have one calculation for your PhD thesis. So it's possible. If you use the fastest computer at that time in Germany, the SuperMUC, it would take 3 days. But then you have to remember that that's one possible realization. We have a turbulent flow field. Normally we have to perform the calculations with small changes in the initial conditions to examine these effects more in detail here. So you have to perform several calculations with nearly identical initial conditions. So it still takes some weeks until you get your results. Then you have to consider the costs. Okay, if we think about the investment of such a computer, there was a calculation that one day cost 120,000 euro. So for one calculation, this cost 360,000 euro. So of course you can apply for it. There is a competition to get access to the SuperMOOC in Germany. You have to write a proper proposal. But the question, of course, is can we do this with a simpler setup and get the same outcome? So when we look here at the direct numerical simulation, so again, the temperature change is a function of the coordinate. Reynolds average simulation would give us this flat profile. So we have an average value of temperature. If we use LES simulations, it's get a little bit finer, so the cores or the larger vortices are resolved, and the smaller vortices are again modeled. So LES, okay, looks better, but still the fine fluctuations are not resolved. And what we then can use as an alternative is to solve the transport equation for the probability density function. So along this profile, we look at the probability of the system to be in one specific state. So we do not have a discrete value. We have an average value, and we have an variance of this value. So we have mean values, we have the covariances, and we also have to consider the chemical source term. And I do not go into the details here, but the advantage of this PDF setup is, okay, we have a physical space here, where we have a fluctuating velocity field. We have a velocity space here. We have this scalar space due to chemical reactions. We have this velocity space due to viscous stresses and pressure fluctuations. And finally, we have the molecular diffusion here. The advantage now of this PDF setup is that this part here is closed. So we don't have any assumptions using average temperatures. And as you know, chemical reactions are very sensitive due to the Arrhenius equations we have with respect to temperature. But so this is a closed system here. Of course, we have some other quantities which are not described very well. For example, here the mixing part here. So we have to model other quantities, but we know the chemistry very well. So and one solution is to use a classical Monte Carlo setup. So we have a lot of virtual particles which are described by our equation system. So each of these particles is a realization of the media we have, the equation system we have. Okay, unfortunately, this is not running. Okay, we see how to continue. So then we can use the simplification of the chemical system we have discussed in the past lecture. So I've shown you that we always reach an equilibrium independing on where we start. And of course, we have to separate between the fast and very fast processes. But we can describe the system normally with 1, 2, or 3 parameters. Here we have water, enthalpy, which we use then to describe the whole chemical system. So we just need to know these two quantities here, so phi and h, to calculate all other quantities. So it's, of course, then a reduction concerning the computational costs. Okay, and then we have some extension of the diffusivity here, which I do not want to explain today in detail. So how can we use this for our simulation? So we have a 2D grid here. So we assume that we have a cylindrical setup here. And we have an outflow velocity here of 300 meters per second for this example. And the composition at the outlet is hot burnt gas, which flows out of the nozzle. Then there's a slow co-flow, more due to numerical reasons. So we have hot gas flowing out here, cold gas here, and then of course this mixes with the unburnt cold mixture here in front and with the co-flow. So now we see the outcome of such a simulation. So we see now the plot of mean temperature and mean H mass fraction. So the flow is coming from the left, going to the right, and we want to see does an ignition occur or not. So you see here the hot flow leaving the nozzle. So here with a temperature around 1350 Kelvin at the outlet. So there are no H radicals visible, so it's hot exhaust gas. And then it continues. So we can analyze, for example, the distribution. So we have virtual particles, which represents the solution of our equation system. So here we can, for example, examine the distribution of several quantities. And what you see here is the hot gas mixes with the cold gas. It cools down. But finally, here at the tip of the jet, an ignition occurs. So we have a formation of radicals here. And then, of course, in temperature increase in the whole system. So again, outflow of hot gas mixing with cold gas, chemistry starts to take place, and suddenly an ignition occurs. And this, of course, depends on the mixture composition, the temperature, the outflow velocity, and so on. And the question is, do we see an ignition, yes or not? So what is the important thing? So, for example, as you see, the ignition takes place at a given distance. This is something we have seen also with OH lift measurements. So what we have seen here with the H radical, we have seen with OH lift 2. With Schlieren experiments, we see the hot gas flowing out of the nozzle. But when we look with a laser inside this hot gas jet, we nearly don't see any OH radicals. And suddenly ignition occurs at a given distance from the nozzle. So there where the flow field, of course, on the flow velocity is smaller, the shear strength is smaller, and so on. So, for example, we have macro mixing due to the turbulent entrainment. we have micro mixing, so dissipation of local composition fluctuations, and we have a local ignition in a specific volume. The question is, does it lead to a global ignition? So at the beginning, when we look at the progress variable, we have only two status here. So we have unburned and unburned gas and hot exhaust gas. And of course, with macro mixing, this does not change. When we consider macro mixing, we see a lot of intermediate spaces. And if we also have ignition, we can see how this does change to the progress variable. So the question is, where does ignition occur? So outside a certain composition range, ignition is very slow. So it's only possible when the unburned mixture is measured, mixed properly with previously ignited particles. And then we have an accumulation of local ignition events, finally leading to a global ignition. So, and when we look, for example, at this specific configuration here, the question is, of course, where does the ignition take place? Is it more at the tip, or is it more at the side of the jet? So, and these informations, of course, we get from our simulations. So the ignition is, concerning these probabilities, more likely at the tip of the jet. So the ignited local mixtures survive long enough to yield to an global ignition finally. So here in this hot region, we also can see that local ignition may take place, but the shear stress is so strong, the mixing with the cold surrounding is so fast that there is no global ignition. This has to happen here at the tip of the jet. So this can then be used for hydrogen cases and propane cases. And you see here hydrogen reacts much earlier, much faster. So here after 460 microsecond ignition has occurred. In case of propane, much more time is needed. And this explained why case of hydrogen, we can use we need to use much smaller diameters to quench a flame. Because after we exit the nozzle, it ignites very fast at even very high flow velocities. So here we have 300 meters compared to 50 meters per second. Propane is quenched easily or reignites very with high difficulty. So it takes a long time in a slow flow field until reaction occurs. So if we decrease temperature here or increase velocity, we won't see an ignition at all. So this is the case why hydrogen, with respect to safety, is so difficult to handle. It's easily to ignite, and it ignites at much worse flow field condition compared, for example, to propane. So then, of course, with this tool, we can analyze the different time scales we have, and we see that at the tip of the jet here, the reactions come in the range of this mixing frequency. So until now, at this position, the mixing of the hot and cold gas dominates the system, and suddenly reaction becomes important, and the system ignites. So we can use a proper PDF setup here to simulate turbulent low Mach reacting flows. And for this example, we use it to examine the ignition in a premixed hot jet. So the ignition appears first at the jet head vortex. So this is what we have seen in the experiments too. And now we can explain why it has to happen. As I said, that's the competition between mixing, cooling down the system, and chemical reactions leading to ignition. And this has to take place at proper locations, and this is again at the jet head vortex. So the interaction between macro mixing, micro mixing, and chemical reactions is of course important, and we can examine this in detail with this simple setup. And the advantage is the PhD student who has done this work has not needed 190 years for one calculation. This was done in hours, so it's quite fast with a sufficient outcome. So with this, I would like to end this part of the lecture. Do you have any questions?
Yes, actually the time and that spark plot, time and the ignition delay plot, that is on different spark conditions that the plasma conditions.
You mean something like this?
Yes, yes.
Yeah.
So does it indicate that we are going continuously on adding energy with due respect of time, and at a point we are stopping it, or
Who is stopping it?
means that increasing plot?
Yeah.
That does it indicate the addition of spark to that?
Yeah, so what we normally have, so I have to check, so here you see it. So normally when we simulate an spark ignition, so we have a continuous energy deposition.
Yes.
Along the whole spark time. So we heat up the system for a specific time.
Okay.
And here the spark ends. And depending on the energy deposition, it can ignite during this time. It can lead to no ignition. Or like in this example, we have an energy deposition. Then the system cools down, but of course here chemistry already has started. So here a lot of reactions still occur, and finally the system ignites.
Okay.
This, if we would use here a straight line, this would mean we continuously deposit some energy into the system at each time step. Now we have modified this in a way that we have only energy deposition for a very short time, for 100 nanoseconds. So energy deposition, some microsecond, nothing happens, energy deposition, and so on. And here we have, I think, 30 of these small sparks.
Okay.
Yeah.
So
But again, this is just here we don't have any plasma effects. We have all the energy put in the source term representing the spark, the heating of the system. So if we use this with a continuous setup, the shape would be identical. So the final temperature would also be identical.
okay, usually what happens in internal combustion engines, after a certain time interval, we go on adding the spark for each cycle. Okay, for each charge, for each fresh charge taken, so we have to spark it. Okay, but here if we go on continuously charging and even after we are stopping it, then is that energy sufficient to carry out the activity? or it is just only to cross the threshold, a threshold value?
So again, this black curve represents a classical spark. Here we have modified the equation that we have discrete energy deposition. So we have energy deposition, no energy deposition, but the integral is identical. The amount of energy we have deposited to the system is the same. So the black curve is a classical spark, more or less. So if we use such a spark, it would ignite our system.
Okay.
So of course, in a combustion engine where we have a turbulent flow field, we need higher energy. But this is something like this. So we have for a very short time our energy deposition.
Does it mean after this again this cycle will be repeated?
It can be then of course repeated. So in a motor, you may not only have one spark, you have maybe several sparks.
Okay.
Or what we have seen here, as I've said, you can use something like the upper image also in a motor. There are existing solutions for this. So you this of course takes some time, but it's incomparable in the time range compared to the length of a classical spark.
So to go into this plasma state, it usually generates and associated with higher temperatures, usually. So here approximately it happens at nearly what temperature range?
Yeah, so we don't have a classical plasma here. So
Okay.
of course, when you look at a spark ignition, you have to consider a lot of physical and chemical processes. I think I have it, unfortunately, only in German. I have to check if it's included here. Yeah, it's unfortunately only in German. But you see here the time scales for different processes. So I will explain it to you. So at the beginning, there's a formation of a streamer. There are different models, Townsend model also to describe this. Then you create this plasma which heat up very fast. Then you have an expansion of this plasma, and then you have normally a shock wave moving away from this plasma. This normally is not resolved in our calculations. We just deposit energy leading to a temperature rise. So we do not bother about this. So it's sufficient if you want to focus on the chemical ignition processes just to deposit energy into the system, because the Arrhenius equation dominates everything. So the temperature is the most important quantity, and all these other effects, more or less can be neglected if you look at a classical spark. Depends, of course, what you want to know, but for normal ignition of an unburned quiescent mixture, the temperature rise is the important factor for a classical spark. But we don't have a classical spark here. We have these streamer discharges, so there is no breakthrough. We don't have a hot plasma channel here.
So usually in internal combustion engines, we have the spark at a single point.
Yeah.
Then that flame front it propagates. So means does it have some effect if we put it the sparks in terms of seeds or in terms of volume? Means which one is beneficial? So as for you, means it's a single spark is beneficial, or multiple sparks, or sparks in terms of seeds, means in the lines, or in terms of volumetric spark? Then which one will be more beneficial, and how it happens?
One of the ideas was to use to have a lean mixtures to reduce NOx formation. And the problem with linear mixtures is that they are more difficult to ignite. So in your combustion volume, you have, of course, very strong turbulent field. So that you have your spark, you maybe have a local ignition, but then you have an extinction. As with these linear conditions, the temperature is not so high, the velocity is not so high, and so on. So it's more difficult to ignite this mixture. And one possibility to get rid of this problem is to use large volume ignition, either using this turbulent hot jet ignition or these non-plasma configuration. So you can see you can reach an ignition in the whole volume. So you have faster reaction because there is more consumption per time, and you have higher probability of having ignition at all.
Okay, we are having starting with a spark, then we are going towards the ignition, then the combustion process.
Mm-hmm.
Okay, so how to know the local ignition and the transition ignition and then the actual ignition process is started? Means is it from the pressure data or is it from anything else? Means when to know that it has converted from the spark towards the ignition phase?
What do you mean is how to know?
Yes.
In addition to that, like when there is a initiation, spark is initiated,
Mm-hmm.
then spark propagate, flame development happen, and then flame propagate.
Yeah.
So to identify that, we are actually looking into the pressure data. So like when pressure rise happens because of two reasons in SI engine combustions. It's because of the change in volume. When the piston moves, volume changes and pressure rises, and again because of combustion. So we have to filter out these two data separately, and we have to identify at what point exactly the combustion will happen, looking into pressure rise data. So how to separate those two things?
You have also an additional effect. You do not need to know only when ignition occurs. You also have to consider the pressure rise, so how fast the combustion takes place. So this is what you see also in your pressure curve.
dp by the d theta.
Yeah, that's
Rate of pressure rise.
the second important factor. And the question is how to filter this. I have no proper answer. So in your pressure curve, you see either ignition has taken place or not.
So in the last yesterday's presentation, you have seen like we are looking into something called mass fraction burnt, and we are calculating it from an equation, which is a standard equation. So once we are calculating mass fraction burnt, we have a range of like 0% to 100%, and we are assuming that if the mass fraction burnt duration between 10% to 90% is happening, that we are calling as rapid burn angle. And from 10% onwards, we are assuming that the actual combustion is happening. 0 to 10%, the stages like flame development and propagation happens, and actual combustion starts happening from 10% mass fraction burnt up to 90% mass fraction burnt. So this way we have done the analysis, but we cannot able to strain the pressure data, like which pressure is able, which is because of the rise in compression, rise in change in cylinder volume, and which is because of combustion.
Why not? So when you use, for example, nitrogen in your system or pure air, you can see the change in pressure due to the compression.
Yes.
And this you can compare with the change in pressure having also a combustible mixer inside with an ignition event taking place. So you should be able to separate then with this non-ignition event in the background between compression and pressure change due to combustion.
Yes, that can be the solution.
Yeah.
In all of our analysis, we are in a process of decreasing the ignition delay.
Decreasing the ignition delay.
Yes.
Yeah.
Means whatever we have studied, so we are always telling that we have to decrease the ignition delay time. Means, is there any cases where this ignition delay may be increased and it will be beneficial for us?
I think for your specific setup, no, because if you increase the ignition delay time, there's more time for disturbing factors like mixing, cooling down your hot volume.
Yeah, no, I'm asking in general in the combustion field or in any of the combustion analysis part. Is there any case or is there any requirement of increasing ignition delay, which will be beneficial for the combustion approach?
Now, normally, if you want to have in the combustion process, it should be an efficient combustion process. There's maybe one reason you want to reduce NOx formation. For example, if you consider this turbulent hot jet ignition, so you have a volume where you ignite your mixture with a spark, and you have a volume which is ignited by the turbulent hot jet flow, like we have seen it here on this video. When you use stoichiometric mixture in the small vessel, it's perfect for the ignition, but you also produce a lot of NOx. Then it's better to use leaner mixtures there too, which of course then leads to longer ignition delay times. With this respect, it makes sense. So you do not use the optimum setup for ignition with respect to the ignition process, but you use the optimum setup to reduce the amount of pollutants, for example.
Yeah, mostly it will affect the speciation part, means how the afterburning products are being affected.
It depends on your specific configuration. So I'm not an expert for gas turbines, for example. There may be also necessary not to use the optimum processes concerning combustion efficiency, but you have to modify the system to reduce pollutants. So it always depends on the configuration you examine.
Okay, thank you.
If there are no further questions, so we can close today's session. So thank you.